Yo, welcome back. Hello everyone, welcome back to another video. In today's video, I'm gonna be covering some topics which might have been left out in the complex numbers because this topic has a lot of subtopics. So I'm gonna try my best, okay, to cover all the topics. And the first one that we missed is angle rotation. So I already discussed graphing, but yeah. And I just want to do a quick little note. This origin right here. This is the origin, right? So the origin right here. This is the origin, okay? And this. And the origin represents the points 0, 0, sections here, okay, to represent complex number would be 0 plus 0 I. Okay, take a look. So this point right here, it acts as a 0, 1, 2, 3, 4, 5, and here minus 0, minus 1, minus 2. Here it acts as 0 as I, 2, I. Here minus 0, I. But we don't write 0 because if you add a number to 0 or subtract by 0, the result would be like nothing. So like here. Okay, I'm just gonna delete this to make space. I hope you just remember that. You can look back in the video, of course. Okay. So yeah. Okay. I'm gonna put the line again. Okay. So yeah, now I made the drawing a little better. I used a scale. But yeah. I'm gonna track it. Now look. So what is angle rotation? What I mean by that is, like, if we have something like 4, if we multiply this by minus 1, we would go from here, we would go from here to here, and this is a 180-degree rotation. Okay, so this is a 180-degree rotation. Okay, and similarly, if we multiply this by minus 1, again we would get back, we would come back to 4, okay, which would be 180 degrees. No, which would be a total of 360 degrees. Okay, because first we multiply this by negative 1 to go to minus 4, then we multiply it by minus 1 again. We're gonna add another 180 degrees, and then do that, it becomes 260 degrees. Okay, but now we didn't discuss what would happen if we rotate it by 90 degrees or 270 degrees. So that's the whole point of angle rotation. Now, now let's look deeper into this. So suppose we can take any number, okay? So since I did 4, I'm gonna do 4, okay? So take an example. I have 4, okay? This is the point I'm taking, 4. Okay. Now, if I suppose that I multiply this number by I, then I would lead to this, which is 4i. So what I'm doing is by multiply 4 by. So if I multiply 4 by I would be this, and as you can see, when we land on this, you can see that this is on 90 degrees. Okay, So this has become a 90-degree rotation. Yeah. So when we multiply 4 or any number or any real number. I'm just gonna take example. When we multiply 4 by I, the number gets rotated by 90 degrees to land on 4. Understand? What it means is that like because you can see this here, like if you want to, like if you put something like we land on this, right? So you can think of this as a line here. Oh yeah, look. The reason this is because when we have a 90 degree angle, look at this. This is 90 degrees, right? This is 90 degrees. Because look, this is a right angled like type, because when you put this, it becomes 90 degrees, okay? Understand? That's why we do that. Now, suppose if I multiply this by I again. So if I multiply 4i by I, what would I get? 4i times I is 4i squared, I squared, and -1. This will land to be -1. Yeah. So okay. Yeah. What would happen is we would land if we multiply this by I. Then what would happen is we would land on this. Okay, I'm gonna make this a little straighter. 1 second. So you can see when we do that. Okay, and then here. Okay, here. Now look, this is the point that we have. So when we multiply this by I, again, we're gonna land on 4. And as you can see here, this is a 90-degree angle. Yeah. Okay. So yeah. So when we add this total 90 plus 90. So I'm gonna write here. Okay. Right here. That. Okay. In this way, this is okay. In this way, this shows the process rotating by 180 degrees gives -4. And why did we prove it? How did we do that? We did it with the help of the complex plane, which is the beauty of math. And without this, we couldn't have proved this, because it all starts with I, you know. So yeah, that's basically the whole point. And like, yeah, that's what happens. And now, okay, now just suppose I multiply this by I again. If I multiply this by I again, I would land on this. And look here, I got another 90-degree angle. Yeah. So this is later. So yeah. Yeah. So total. So in total. Yeah. So already in total, I'm writing this for this part. Yeah, because 4, when you convert 4 to -4, it becomes 180 degrees. Because if you multiply this by I, this is 90, and here again under 90 degrees. When we add it, we get 180. Now at -4, if you multiply this by I again, we'll land at -4i, which is another 90 degrees. Let me put it here. And a total another 90 degrees. Okay, so I'll write in total 180, in total 270 degrees. Okay, so yeah, so in total 270 degrees. Okay, because we have to add this 90, because 90, 90, 90, 90 degrees. So when we take for 270, rotate it, when we rotate for 270 degrees, we're down to -4. Now, again, okay, now let's do this again. If I have a number 4i, I'm gonna multiply this by I again. Okay, yeah. If I multiply this by I, I'm gonna land on 4. So from here, I'm gonna go from here to here, which again shows a 90-degree angle here. And guess what? This is 90 degrees, and in total 360 degrees. So look, this is what happens. What we did was we multiplied each number by I, the imaginary unit, and look, do you see this angle right here? These angles, they're like, this is on this side, that's on this side. These, like, it looks like a little pattern, right? Like on this side, this on top, this bottom, this top, this top. And that's the beauty of math. Now look what we got. So this is what happens when we rotate. So yeah, I'm gonna write, when we rotate a number on the number line by 90 degrees or 27 degrees, it lands on the number in a complex plane. For example, rotating a number x 90 degrees gives, if you rotate it 90 degrees, gives xi multiplying by I, and 270 degrees gives, would give minus xi. Multiplying by I again. The 180 degree angle. This is the summary of what happens. I'm just gonna block this here. Okay, now I'm gonna write something else. So yeah, complex and imaginary numbers can be thought of as angles in this manner. As angles, they can be thought of as angles. Like for example, like in this case, I would be almost 90 degrees. Because if you multiply this 90 degrees, we multiply I at 90 degrees, and I squared would give I squared, like if you multiply by I again, it would be 180 degrees, and like, and again, I cubed would give 270 degrees, and so on. So it can be thought of in this manner. It's not like in a classical sense. So yeah, just take an overview of this. Okay? Just map it all out, you know. So this is the beauty of math. See, imaginary and complex numbers are not just imaginary. They're also related to geometry, angles, you know. So I hope you understood the process with me explaining on the whiteboard, me talking out, you know, like, and also the complex one extends to infinity, but I'll be second with them. So yeah, also suppose we do this counterclockwise, like if you have -4, if you multiply this by I, we're gonna get here. If you multiply this by I again, so but if you multiply this by from I here, it would be 90 degrees here, not 270. But if you would now you will get here, and if you multiply this by I again, it would be 180 degrees, not 260. So that's how converting 4 to -4 or -4 to 4 would be like a 180 degree rotation. Okay, so yeah, and from here 180 degrees, then here it will be 270 degrees. If by adding 90 degrees, then here 360 degrees, and we would land back here. So we can do it vice versa. Okay, understood? So yeah, that's how you do the process. Okay, and yeah, let me write it here. Yeah. Alright. We can do the rotation negative numbers from the negative side also. Okay. Yeah. And also remember this. But in the end, we will land back on the on the original number at 360 degrees. Okay? Degrees. Yeah. So just remember all these points. I'm explaining it in detail because this is an important topic. I shouldn't have left it out, but now it's handed to you. So yeah, 270 and 90 degrees are imaginary, but 180 degrees, 180 degrees, like when we rotate it by 180 degrees, it's the additive inverse. The additive inverse is the number for Jacobs, so you know that. And yeah, so these are all the notes. And yeah, you can also do it, you can also start with the imaginary line. Like for example, if I start from here, if I multiply this by I, you get -1. Multiply this by I, you get -I. And multiply this again. Oh yeah, another thing. So, okay, I'm just gonna write this here. Look, suppose if I start from this point, I. We can also start from imaginary sections. Okay? Yeah. Let me write this here. Rotations can also be done in the imaginary section. Okay? I didn't write this. This is real. I forgot to write the starting. That this is real. And this is, yeah, you know that. This is a real imaginary. So now, if I start from the I, if I start here, if I multiply this number by I, then what would I land on? -1. And if I multiply this by I, I'll land on -I. If I multiply this by I would just, I would land on, -I times I into I would land on 1, right? Then I would land on 1. And if I multiply this by I would land back here at 360 degrees, okay? So, and similarly, if you do from 2I, multiply this by I, we'll get a -2, then we'll get -2I, then 2, then 2I. So yeah, you can, like, if you do from here, you can do here, then 90 degrees, and 180 degrees, 270 degrees, 270. Oh yeah, one more important thing. When we're, okay, I think I should mention this. Okay, yeah. When we rotate and angles, imaginary section, the angles 90 and 270 degrees land us on the real numbers, and on the imaginary. Okay. Now I have to box this. This is so important. Hey, I don't think you can see it. 1 second. Okay, no worries. I'm gonna put this down here. And okay. Okay, here. I can put it here. Sure, 1 second. And one more important thing is that put this in purple. Yeah, I'm gonna box all these points. Make sure to keep these points in mind also. Okay. Okay. So I'm gonna make this. These are the points outside of the, oh yeah, remember this also. All of these are important. The ones, this is related to the process of how I'm doing this. These are the boxes. And yeah. Okay. So yeah, I think that's it. But okay, let me see if there's anything left. Okay, 90 degrees. Yeah. Okay. So suppose if I yeah, I think that's all. That's basically the overview of that. Okay, now just keep this, like, yeah, when we rotate angles from the imaginary section, like suppose I have 2i. If I multiply this by I, I'll get -2, which will land us on the 90 degrees. But in this definition, when we do it for the real numbers, 90 or 270 degrees lands on a number, lands on an imaginary number in the complex plane. Yeah, it lands on an imaginary number. Like for example, 4. If I multiply I, my 90 degrees will get 4i. But if I have something like 4i, if I multiply this by I, I'll land on 90 degrees. I'm gonna land on -4. If I rotate this one, if I rotate this 90 degrees, I'm gonna land here. Okay, understood? If I because I square -1. So. But here, for real numbers, it will be answered. Similarly, if I do if I do it for 180 degrees, if I multiply this by I again, I'll get -4i. I'll get -4i, 180 degrees. But for real numbers, 180 degrees gives a real number. But here, imaginary numbers. But if I multiply this by I again, I'll get 4. I'll get 4 here. From this point to this point, there'll be 270 degrees. Okay? But in this definition of real numbers, it would be imaginary. But in this case, it's real. And if I do 260, if I do it 360 degrees, I'll land on the same number, just imaginary. 360 degrees. But if we do 360 degrees in the real numbers, we'll land on a real number. So it's all vice versa. You know what I'm saying? Okay. So yeah, I hope you understood this. Okay. Oh, that was a big topic. All right. So now, okay, I think that's a lot. It's a lot. Yeah. Okay. Damn, bro. That was a lot. Yeah, just make sure to know all these. Just remember to watch my videos and stuff. If just keep rewatching the videos. If you have any problem, you can let me know. But you know what I'm saying? It's all vice versa. You know, with it's vice versa. Yeah. So what this means is that it's vice versa when we rotate numbers in the imaginary section. Okay, like you know the real and complex are mixed. The real, if you like, you know, yeah, you get the gist. Okay, it's all written. I explained it already. Okay, so yeah, I think that's all. Okay, so yeah, I'm gonna have this out now. Oh my god, that was so much to do, man. Yeah, just note all these. Oh yeah, also rotation can be done. They can be done for any number you can start. It can be negative, it can be positive. You can try, you know. Yeah. Okay. Oh my god. Yeah. Okay. Now, let's do something. Okay, I'm gonna do a mixing session. Imagine a subset. So when I get this misconception like here, because look, thing is that if we have like what are the complex numbers where b is real and I is imaginary. Okay. So now we can do something. If you look at these two here, look. Let's split this. That's my plan. Yeah. Okay. So no, I think I should take the topic. Hold on. Actually, the topic here. Okay, no, this is right. So this will be bi, and this will be a plus bi. However, we can rewrite this as 0 plus bi. This fits the definition because this is our a, this is our b. So we can say that these are equal in form. Okay, so we can like what I mean by this is that we can represent this in like a, for example, if I have something like 5i, can't I write this as 0 plus 5i? Yes or no? Yes. And if I have something like square root of 2i, can't I write this as 0 plus square root of 2i? Yeah, we can. And if I have something like the square root of negative 2 times I can write this as 0 plus I into root 2 into I, and to simplify this, I squared negative 1, so plus minus 2 plus the negative version of the square root of 2. Okay, so what I'm saying this is that imaginary numbers are basically complex numbers. However, the real part is 0. Keep this in mind, that they are basically the same thing. They're the same thing. but the form is 0. And yeah, imaginary numbers are a subset of complex numbers because complex numbers have a real part and an imaginary part. Okay, and imaginary numbers, and also real numbers are also a subset, of course, because yeah, real numbers are also a subset. Because subset means the numbers which are consistent inside of that. Okay, the numbers which are consistent inside of that. Like, okay, now let's do one more. Alright. Okay. Okay, now I'm gonna give the true reason why complex numbers can't be compared with any number. Okay. Now look here. I made a short video where I said that they can't be compared, but I felt that the reasoning I gave was not too strong. So what I'm gonna do is I'm gonna give a strong reason. Okay, look. And now look, first, let's talk about comparing real numbers. Comparing real numbers. Okay, let's see. Check. Okay, this is a little question. Here, check this out. Okay, look, this is rational, irrational, integers, whole numbers, paired with each other. So look, okay, now this is whole numbers, and these are, let's write natural numbers and irrational numbers. Okay. So these are a list of numbers I gave, and you have to see whether they can be compared. Like, so look, a common misconception I see is that many people think that rational numbers are separate number system. Irrational are separate. Integers are separate. No. All of these number systems, they are a part of one number system. All of these, they are part of real number system. Okay. So since they are all within one number system, they can be compared. Like 5 can be compared with the square root of 2. This is greater. Okay. 0 can zero is an integer. 0 can be compared with 0. Yeah, they can be equal. Yeah, and natural numbers like 1, irrational numbers, square root of 2. Yeah, this one. This is greater. Okay, so they can be compared. Why? Yeah. Okay, so let me give the reason. The reason is, yeah, real numbers. Okay, now here's the thing. Real numbers. Okay, real numbers consist but since number systems, like for example, integers, or natural numbers, rational numbers, irrational numbers, okay, of number systems, and they in fact compared with each other, since they all are a part of system. Okay, all of this, all rational whole integer, they all are literally a part of one number system. Okay, a part of one number system. Okay, so yeah, that's basically like, so like that. I just want to close it up. Now let's look at complex number systems. Check this out. Main two number system. I'm saying main because actually we have a lot of number systems, but that's for another video. Like we have quaternions, octonions, but that's not for today's video. Okay, so look, real complex. See, these the complex. See, look, complex numbers. No, are complex numbers a part of real number system? No, these are separate. We can't say we can't compare them. No, we can't do that because because they're separate. See, complex numbers are a whole are a group of a whole entire are like complex numbers. The complex number system is a whole new number system which is not consisted within real numbers. For example, I, 2i, 3/4i minus 4/3 minus 3/4i are not real numbers. That's because, but 5 is a real number, 6 is a real number. Yeah. However, 5, 6, 7, minus 9, etc. are real numbers. Okay? Understood that? Hence, in this way, okay, here's the big part. Hence, in this way, complex numbers and real numbers cannot be technically compared since they both are involved in separate number systems. That's the thing. It's about number systems. Okay? And I'll give another reason. Let's see if it sticks with you. Another reason. Okay? So look, now one more thing. So look, think of the imaginary image I as a variable. Just think of it. The square root of technically been assigned a variable I, also known as IOTA. Okay. However, since iota I is used with every complex number simplified form. Simplified. Simplified. Since I doesn't technically show a meaningful meaning. Okay, I hope this makes sense to what this means. Like the square root of -1. If you have to compare this and this, but like how would you compare it? First, you have to evaluate this, right? If you evaluate this, you'll get 1, but this is I. But isn't I like a variable? How would you compare this? It can't be compared. Like, just think of it as a separate number system, okay? Look, yeah. And complex numbers cannot be compared with other complex numbers, since they cannot be visually seen. Unlike example, 2/3 can be expressed as 2 slices in a pizza with 3 slices. Like, what I mean is, okay. However, it's not possible to compare 5i pizzas and 4i pizzas. Can we do that? No, we can't do that. We can't say we have 5i. I have 5i pizzas, because I is like imaginary. Like, imaginary is something which is not real in the number system. Okay, because like if suppose I have pizza. This is a bigger pizza. 4 is bigger than 5, but because of I, everything is going out of place, because we don't know if I is 0, 1, 2. Like, what is it? How we can? There's like 0 by 0, 0 by 0. 0 by 0 has no agreement, right? In the same way, complex numbers, they don't have any agreement. Complex numbers, okay. Complex numbers practically don't have any agreement with real numbers in compare. Like, just think of it like real numbers are a separate thing, complex are separate. Don't jumble them up. If you want to compare a number, it should be within that number system. A number can be compared within its number system. Okay, understood? So these are the main points. But yeah, of course, the modulus of a complex number can be compared in fact. Okay. Yeah, I already mentioned that in a previous video. However, the modulus number can be compared with other numbers, real or complex. I already explained that in previous video. Okay, it's in the short video. Note, complex numbers can't be compared. Just state it out. I also gave some examples which can be compared. But this is the real reason. Okay, wait, I don't think you can see that. A number system. Okay, just look at this. I want to make you see everything. Here, this is what this says. Okay, and this is all the reasons, okay, why they can't be compared. Okay. Oh my god, this video is long, bro. Yeah. Damn, bro. So that's why they can't be compared, bro. Because, you know, like, I hope you understood, okay? I just, okay. Now I want to go to another topic. Okay. Wait, do I even have time for another topic? Oh my god. Okay. Yeah, let's see. Also, one more thing. Okay. An important note in graphing. Complex numbers in the complex plane. Complex plane. Okay? Plane. Oh, okay, let me write it. Okay. Okay. If you are graphing, if we graph, hold on. Wait, what was I going to write? Here. If we graph, okay, yeah, hold on. Like, oh yeah, but I remember. Graphing complex numbers with irrational codes. Example. Let me give you an example. For example, the square root of 2 into the square root of 2 plus 3i. 3i. And then one more. Let's say we have 5 minus the square root of 3 into I. 3i. Okay. Can it be graphed? However, there won't be an exact graphing point, but since they are irrational numbers, but we can approximate and put the number in between two numbers. Like, for example, if you have to graph this, okay, important. If you have to graph this, square root of 2, this is around 1.417. So put this, so you have to put this. Yeah, this has to be in between 1 and 2, but there won't be an exact graphing destination. Okay? Like, I'll just draw one more time. For example, if I have something like a, okay, let's do it. Like, for example, you have to do 1, 2. I'm gonna graph here, circle this area. This should be the square root of 2, just in between. Okay, this should be the root 2. Okay, root 2. And then we will just graph the other complex number. And suppose we have 3i. We have negative 3i, right? Okay. So go down here. Suppose we have like, so square root of negative 3. The square root of negative 3 is what? 1.73 blah blah. Okay. Now this is between 1 and 2. So look, the thing is 1.41 is closer than 1. So what you should do is you have to put this closer to 1. Okay. You have to put this closer to 1. Closer. Here, like a little closer. Like, yeah. And place the number. Place the irrational value place the irrational value closer to the number which it is near to, which is nearest to. Yeah. Like for example, square root than 1 to 1, so it shall be put close to 1. Okay, got this? Just remember this. Okay, so like this, check. Okay, I'm just gonna show you this. You can't see it. That's what this is, but you can't see it. And now you can see it, right? Yeah. Okay. So yeah, like for example, if I show in this graph, you have to put it closer to 2, and same goes for like this minus the square root of 3i. Suppose this is a negative I, and this is negative 2i. In between, we know that there are infinitely many numbers in between any two numbers, but I'm just putting a gap to show you, but don't put a gap in between. Just leave a small gap if you're writing this in exam. So I want to do is I would want to put it closer to this, a little no, but in this case this is closer to what? This is closer to, oh no, this is negative, right? Negative. Yes, negative. Okay, look at this is negative 1, this is negative 2. Yeah, so I think you should put it like we have negative 1.7 and negative 2. So yeah, this is closer to what? This is closer to negative 2. So I would want to put this, I would want to graph this here. Minus the square root of 3 into I. This is where that would be closer, okay? Okay? So yeah, that's where that will go, okay? So I hope you understood the concept of graphing rational numbers. Yep, but there won't be an exact point, but you can approximate it, of course. Okay. So now, oh my god, okay. Yeah. So okay now. Let's see what's new. Okay. So now, okay, I don't know if there's any topic left. Oh yeah, wait. Oh yes, hold on. I think that I have to explain the integral powers. Wait, do we have time? No. The integral powers x is odd, 2n is even, integer, or however you pronounce it. Okay, so then this will mean there will be two cases. Ix would either be positive or negative I, and I squared, and I mean I to the 2n would either be plus minus 1. So this makes things much easier, because then we would have to only assume only two choices. Okay, so like suppose we have to find something such as I raised to the power of 87. So we know, suppose, take a look, we know if you have a question that says find whenever we the result. Okay, wait, after four numbers, like when we get the result, power, we take the powers consecutively, 1, then 2, etc. We would land on the same result. I explained that, like, for example, I already explained that, like if we have something like we have I0, I1 is I, then after 4 times, so 1, 2, 3, 4, this will be I. Check it's true. Okay, so yeah, this is how to do. Suppose, like, if you get a question that says, okay, okay, so suppose we get a question that says the powers of 87 is odd, the result will either be I or minus I. Okay, now we can break this down to 2 parts. Write this I 80, I 7. Okay. And actually, how would you find this? But like, hey, there's a trick to this. I don't think that trick is difficult, but I think that if you want to try this, okay, yeah. Like, for example, what you have to do is you have to divide 4, or the trick is, trick. Answer. Trick. Divide by 4. Divided by 4. Check it. Okay, look, I'm gonna explain this. First, let's divide this. Subtract 80. 7. Subtract 4. 3. Take it. 4, 4. 1. 20. So we get 21 and 3/4. Okay? Basic math. 21 and 21 and 3/4. Okay? Yeah, just check an answer. Okay. My answer is correct. So now, look, the remainder we get is 3. Hold on. When you divide this remainder, we get 3. So what does this mean? This means that if we have something like this means that we have to find I cubed, which is negative I. So this is equal to I cubed equals negative I. Amazing, right? So just use this trick. The video is almost done. Okay. Okay, what the trick is basically the remainder. Basically, hold on, I'm gonna put an arrow. Yeah. Okay, yeah. Use the remainder as the exponent to find this power, and that's your answer. Bam. Okay. So just remember all these points. Now you can try to practice on your own. Just find some powers with this rule. Oh god, yeah. And that's it. That's all. I think there's one thing left, properties. Properties are very easy. I explained it in my description also. I mean in my channel community post, check that out. Like if Z1, Z2, Z3 are three complex numbers, then you know, like, then Z1 into Z2 plus Z3, Z1 into Z2 plus Z1 into Z3, Z1 plus Z2 equals Z2 plus Z1, Z1 plus the whole of Z2 plus Z3 is equal to the whole of Z1 plus Z2 plus Z3. Like, all the properties hold like real numbers. Like, for example, I'm just gonna write the whole thing. Like, if you have something like Z1 plus Z2, this would be Z2 plus Z1. Same goes for subtraction, and you know Z1 into Z2 plus Z3 equals Z1 into Z2 plus Z1 into Z3. Where these are all complex numbers. So you get the drill. Oh, I just accidentally erased them. Okay, yeah. So basically, sorry, that was a mistake. I didn't forgot to erase it. Okay, the video's okay. It's too long. Sorry. So those are the properties of. Those are basically the properties. You know, they hold. Like for addition. Oh yeah, but of course. Yeah. In the properties. They. All of them. Like real numbers too. Division, which holds okay, except closure property. Okay. These are the properties because like division by 0 is a real number, and that would not give a result. Oh my god. Yeah, I'm ending this video. Just, you know, please like and subscribe. Okay. And yeah, I think I should wrap this topic up. It's been long. I'll see you in the next video. But I'll see y'all when I do. Peace.